Hi everyone, my name is Michelle Duran Chavez. I am a chemistry student and I'm going to talk about the basics of helium ion microscopy for the Imaging at Nanoscale class in spring 2020. The helium ion microscope was reported around 2007 and 2008 as a new type of microscope. It was designed by John A. Note and his colleagues Bill Ward, Nick Economou, Ray Hill, and Alice Corporation, as an alternative to the electron microscope. Instead of using electrons for high magnification imaging, they developed a technique with helium ions. Helium ions have shorter wavelength compared to electrons, so they can form a more tightly focused ion beam. This translates for a microscope in better image resolution. Helium ion microscopy can be very useful in both material science, like for microchips and semiconductor materials, and biology. The idea of helium ion microscopy is not to replace scanning electron microscopy, but for the two techniques to complement each other. A helium ion microscope operates a lot like a scanning electron microscope, but has unique capabilities. The source technology, the sample interaction, and the contrast mechanisms are pretty different. The helium ion source offers high brightness and also a small energy spread, allowing the beam to be focused to small probe sizes around 0.25 nanometers. It can produce images with sub-nanometer resolution, which is up to 4 times better than an SEM. An important fact about this technique is that the images obtained have higher surface contrast and better depth of field, meaning that more of the image is in focus compared to an SEM image, and also sample charging artifacts can be mitigated. Helium ion microscopy can also create images with Rutherford backscattered ions, which are a high-energy helium ions that rebound off the sample, being able to provide information about the chemical composition. Now let's talk about the helium ion source. It can be a single crystal metal in a needle shape. It has a pyramidal structure of atoms with a parabolic end form, where the end has a small number of atoms, around 1 to 7. A large positive voltage is applied to the source and the electric field at the atoms grows to a level of a few volts per Armstrong. When helium gas is admitted close to the needle under influence of electric field gradient, it is polarized and drawn towards the apex. The outer electrons can tunnel out of the gas and into the bulk metal. The region where the tunneling occurs is called the ionization disk. This gas atom, now positively charged, is accelerated away from the ionization disk, so each of the apex atoms creates a beam of helium atoms, and one of the ion beams is allowed to pass down the column and be focused, as it is scanned across the sample. Regulating the pressure of the gas ranges the beam current from nanoamps to picoamps to femtoamps to attoamps, and also the source is reported to be stable and reliable. Helium microscopy is related to field ion microscopy, or FIM, a technology developed in 1955 by Miller and Bahadur to look at individual atoms on a cryogenically cooled tungsten tip in ultra-high vacuum with small amounts of helium gas in it. In the 1980s, scientists created a focused ion beam microscope with a gallium ion source. However, they were not able to capture the best images using this heavy ion, which inspired others to pursue other ion sources. Helium ion microscopy is similar to the gallium technique, but as mentioned before, it has a pyramid-shaped ion source that forms a focused beam. Helium ion beams have higher mass and shorter de Broglie wavelength. Therefore, these ions interact more strongly with materials and produce like 100 times more secondary electrons. As more information goes to the detector, highly detailed images are provided, and also with faster image acquisition for a given charge dosage. The helium beam interaction with the sample is pretty different from gallium FIB or SEM. A Monte Carlo modeling of a silicon sample can explain the differences observed. A gallium beam that is 30 keV will penetrate around 50 nanometers and produce excessive dislocations and sputtering. The excited volume is broader than the incident beam at the surface. An SEM, 1 keV, will produce less damage to the sample, but there are many backscattered electrons and undesired secondary electrons. The helium ions, that are also 30 keV, penetrate a great distance into the sample before diverging. The secondary electrons provide information that is shallow and not broader than the probe. Let's compare these images. The Helium Ion Microscope image shows narrower edges than the SEM image. Also, the image generated will show more contrast. Sometimes, materials can be identified from the relative brightness in the image, and contrast is also important because it can provide electrical, crystallographic, and magnetic information. There are two different ways to utilize backscatter helium ions. Commonly, a microchannel plate is used as a detector in order to acquire qualitative element distribution maps. These images can be poor in topography and rich in element contrast. The second one is a silicon drift detector that can be used to obtain spectroscopic information from microscopic areas. Quantitative element identification is possible in this case, with the same principles as Rutherford backscattering spectroscopy. It is important to consider that high sensitivity is needed from the detector. The backscatter efficiency can be increased by lowering the acceleration voltage, but this will reduce the sampling depth. In summary, this technique provides high-resolution imaging, even of uncoated biological samples. It allows imaging of insulating samples, has high surface sensitivity, allows imaging of ultra-thin layers, and you can perform direct lithography in it. But let's remember that helium ions might damage samples more than electron beams would. And that will be all. Thanks for watching.